Okay. In the previous lecture, we introduced the sugar polynomials, and we are also interested in this structure concept, literature sum coefficient. And as a special case of this, the following theorem is known, also called the PLE formula.
This number, the Littlewood-Richardson coefficient, can be easily computed, or
I will
formula for
yes, I will explain later. Theorem, also called PLE formula. For any partition lambda and the integer k. Since we are considering all partitions, there is no restriction about the partition. The product of two sugar polynomials S lambda and Sk, k is partition corresponding to one row, is in fact S mu. It is the same formula as the case of Grassmannian, where the sum ranges over all partitions mu obtained from lambda by adding k boxes with no 2 in the same column. No 2 in the same column. Or equivalently, the skew diagram is mu over lambda skew diagram mu over lambda is the horizontal strip. Horizontal strip. Size k. The condition is the same as the Schubert classes of the Grassmannian. For example, as already showed, when lambda equals 2, 1, and k equals 3, then product of two sugar polynomials is computed as follows. At 3 boxes. Plus 2 and 1 plus 2 1 plus 1 So the result is S I1 plus S42 plus S411 plus 321, like this. And as I said before, there is a combinatorial formula which determine this LR coefficients. So in the next subsection, little root Richardson rule. And there is a combinatorial formula. For computing the LR coefficient, d lambda mu nu, known as the little root Richardson rule. Before stating the little Richardson rule, we must prepare some notation. First, word over tableau. I will show one example. One example is very helpful. For example, there is a tableau. Given a tableau, for example, like this: 1, 1, 2, 3, 2, 3, 2, 4. Tableau T. Given a tableau T, skew tableau T. We read number from right to left and top to down. Word WT. In this case, we start 3, 3, 2, 1, 1. Next row 3, 2, 4, 1. In this way, we given a tableau T, we derive a word WT. And we need another notion from combinatorics. Given a word W, A1, A2, AN, for each integer R and 1 I, sorry, A1 to N is entries A1 to N is 1 to N, N minus 1. Define Mi A1 AR is defined to be the number of occurrences of the symbol I symbol I in A1 subword A1 to AR. And our W A1 A2 AN is in the symbols in the symbols 1, 2, N is said to be lattice permutation. The definition is somewhat complicated, but not so difficult. For each integer, I will give some example later. The following condition is satisfied. Is satisfied. M1 M1 of A1 to A subword is greater than or equal to M2 greater than M3 and so on. This is lattice permutation. It is called lattice permutation. Note that we follow the McDonald's book, so we read number from right to left and top to down. However, in the literature, for example, Fulton's book, there are different reading. In the Fulton's book, right to left and down to up. So, and he says reverse lattice word. So in some literatures, the convention is different. So please be careful. We follow the McDonald's convention. Over reverse lattice property, reverse lattice word or reverse lattice properties also sometimes referred to Yamanouchi word. Yamanouchi is a physicist, Japanese physicist, Yamanouchi. Japanese physicist, Yamanouchi Takahiko. Takahiko Yamanouchi. Sometimes Yamanouchi word or reverse lattice word. We follow the convention of Magnard. Lattice permutation. I don't know why permutation, but lattice word or lattice permutation. Then the celebrated little Richardson theorem, little Richardson rule, is stated as follows. Rule. Let lambda mu be partitions. Then the little Richardson LR coefficient d lambda mu nu is given by the number of tableau T of shape nu over lambda and content. I defined the content of skew tableau in section 2 content mu such that the word WT is lattice permutation. This is a celebrated little Richardson. Little Richardson stated this theorem in around 1930, but they did not give the precise proof. In late 1970s, this statement was proved by combinatorialists.
If you change the lambda and mu, then it's the
same. Because it is not obvious, but lambda mu nu is mu lambda nu. And also there are some identities in these numbers. And I will give you one example. Lambda 2 1 1 nu 3 2 1 and nu 4 3 2 1. So the skew diagram nu over lambda is like this. Two, 1 1. The whole diagram is new, shape new. And this part is shape lambda. And skew diagram nu over lambda is this box. This box. And we need and the content, or sometimes wait, content mu means three ones and two twos and one three, number three. So, for example, one, the tableau is the number is weakly increasing in each row and strictly increasing each column. So 2, for example, 2, 1, 2, 3, 3, 1, and 2, 2, and 1, 3. Another feeling is 1, 1, 2, 1, 3, 2. There are more feeling. One, one, two, two, three, one. There are more. This is T1, T2, T3. One, two, 2, 1, 3, 1. And 1, 2, 3, 1, 2, 1. One more. One, 3, 2, 1, 2, 1. So T4, T5, T6. These tables satisfy the condition of the semi-standard tableau. Among these 6 tableaus, we must find we must find the tableau which satisfies lattice permutation. The corresponding word is 1, 1, 2, 1, 2, 3. W2 is 1, 1, 2, 1, 3, 2. WT3 1, 1, 2, 2, 3, 1. And WT4 is 2, 1, 2, 1, 3, 1. WT5 is 2, 1, 3, 1, 2, 1. 3, 1, 2, 1, 2. So we must check this condition. in each R, we must find tableau which satisfies this condition. For example, in the case of T1, each stage we check. Okay, lattice. This is lattice permutation. T2, 2, 1, 3. Okay, lattice permutation. And also T3, 1, 1, 2, 2, 3, 1. Okay, they are lattice permutation. However, in the case of T1, 2, 1, 2, this does not satisfy the condition. So this is not lattice permutation. 2, 1, 3, 1.2, 1, 3. 2, 2, 1. 2, 2. あれ
First, A1 is M1 is 0, M2 is
M あそうそう M だそうか not satisfied okay sorry I'm confused not satisfied so there are there are 3 tableaux which satisfy this lattice permutation, this condition. Therefore the little there are some number D 2, 1, 1, 3, 2, 1, 4, 3, 2, 1 is 3. In this way, we can compute the LR coefficients. This is the celebrated little Richardson loop. Finally,
so there must be computing program.
yes, maybe Anders Buch, he studied the quantum cohomology ring of Grassmannian also. Anders Buch produced a computer program in his web page. That's Buch, Danish mathematician. Buch, not book. And that's Buch, Danish mathematician. And finally, I will mention Jacobi 2D formula. First, we define we need some definition. For partitions lambda mu for given two partitions, we define the skew Schubert polynomial. Skew Schubert polynomial. Skew Schubert function. This is no longer polynomial. Function as denoted by S lambda over mu is defined by d lambda mu is LR coefficient. Then Jacobi Trulli formula is stated as follows. For partitions lambda and mu contained in the rectangle of R times n
What is this S lambda slash mu?
is
And this is a skew
skew diagonal. Skew
And then, but you are summing over
all
all new. This is a partition one.
yes lambda skew yes new is all partitions.
But what is the relation between new and lambda and mu? So here new is just the product of lambda and mu, but you are
Yes.
using different. So
Uh,
why is that? Why it is not polynomial?
Because we are considering in lambda. Lambda is
This you are in the class, so it's
lambda
in this limit of.
inverse limit.
I see. And what is the relation between nu and lambda?
You and automatically, in fact, if lambda is not contained in nu, automatically d lambda mu nu equal 0. Or mu not contained in nu. D lambda mu nu. It is not difficult to show this result. So in fact, it is finite sum.
Then do you assume the lambda contains u?
No, we don't. We did not assume. We don't have to assume because in such partitions, d lambda mu is automatically 0. So we don't have to assume this.
I mean lambda and mu.
Lambda.
So you use the rotation
Lambda.
over mu.
Mm.
On the right side.
mu lambda. lambda. lambda いたな。スキューシュアポリノミアル。ラムダ。あ、そうっす。we don't.
Literally, S lambda times S mu is given this way.
Is lambda. Yes. D lambda mu nu. This is a definition of LR coefficients. And using these numbers, we define this polynomial. This is the definition of error coefficients. Using error coefficients, we define this polynomial. And when it follows that if for example, if size I should say more about the properties of little results. For example, it is not difficult to show d lambda mu nu equal d mu lambda mu. The d lambda mu nu equals 0 unless nu equals mu, and by this condition, note that
So originally, lambda and mu varies independently.
yes, independent, yes.
Independent, but since you consider skew one, so lambda, there must be some relation between lambda and mu. That's his question.
So lambda should contain
No.
mu, right?
Well, we don't. We need.
When you model by mu, you are considering skew.
Skew.
Skew. What is the name? Skew diagram. What is this?
Of course. It is. The definition has a sense when mu is contained in lambda. However, we don't have to assume that because if lambda mu.
So why don't you write down that condition there, and
Usually.
remark, and you should add remark. We don't need this condition.
We don't. Why? I don't.
You are wasting time.
あれ？どうだったかな。
The first identity comes from the anti-competitivity.
Lambda mu.
Is it lambda?
Lambda mu lambda. Lambda mu. Kronecker.
Mu what?
Mu
What is
empty. So using these relations, when
Anyway, you claim that there is no relation between lambda and mu.
Yes.
Okay, so let's
sorry. Then for partition lambda mu contained in the rectangle, we have S lambda mu is determinant H lambda I. H denotes complete symmetric polynomial minus mu j minus I plus j. Or equivalently, using elementary symmetric polynomial, conjugate partition I minus conjugate minus I plus j in particular, each sure polynomial is expressed as polynomial. Or E conjugate lambda I minus this is a Jacobi 2D formula.
2D is also
Italian mathematics.
But Jacobi, I think, is not Italian.
Jacobi is German. German mathematician.
oh, there's one counterexample where the name ends with I is not an Italian. So this is probably, I don't know many other people.
Okay, so finally we will give complete discussion of the cohomology of the Grassmannian. So section 5, cohomology of the Grassmannian. Part 2. We would like to describe the multiplicative structure of the polynomial of the cohomology.
Let me see. T lambda I conjugate
T
is
is
the I term of conjugation?
is T lambda I. Yes, T lambda I. Which means T lambda I. Conjugate partition T. Okay, little root Richardson rule. As you might already notice, the structure constant is given by the LR coefficients. So let lambda R ring of symmetric polynomials in R variables. R is a number of variables. And we define an additive homomorphism. Denoted by theta lambda r h star from lambda ring lambda r to the cohomology of the Grassmannian. And as I said before, the Schubert polynomials are basis of lambda r. So each Schubert polynomials length lambda is less than r. We assign a sigma lambda if lambda is contained in the rectangle, and 0 otherwise. At present, it is additive homomorphism, and of course surjective, since Schubert class is a basis of the cohomology. So we obtain an additive surjective homomorphism. In fact, this theta becomes a ring hom, because by the Yearly formula, theorem 3 and theorem 4, 6, and lambda r is generated by complete symmetric polynomial. I forgot to. In fact, complete symmetric polynomial is a special case of Schubert polynomial. I did not say this fact, but when the partition is one row, the corresponding Schubert polynomial is complete symmetric polynomial. So using this fact, theta is homomorphism rings. And we know the properties of Schubert polynomials. So, and we know the relation between these Schubert polynomials. So, by sending the by sending the relation to the cohomology ring, we obtain the relation in the cohomology ring. So, for example, in the ring lambda r, we know S lambda times S mu or D lambda mu nu sigma nu. D lambda mu nu is LR coefficient. And we send this relation by theta. So by definition, S lambda sends to sigma lambda, S mu. Sorry, S nu. And so by sending this relation through theta, we obtain d lambda mu nu sigma nu. Therefore, the structure constant is given by LR coefficient. So we conclude theorem 5.1. The Schubert classes sigma lambda. Lambda is contained in the rectangle. Satisfy the following formulas. Sigma lambda, sigma mu, equal summation d lambda mu nu mu sigma nu. Where d lambda mu nu is LR coefficient. So in the case of complex Grassmannian, we can solve the structure constant problem completely. And finally, we wish to solve the Jamberi problem. Next section, Jamberi formula. We define the ring home. And we know already the Jacobi 2D formula inside this ring. S lambda is determinant H lambda I minus I plus J and we send this relation to the convergence of the Grassmannian. Then become S lambda becomes sigma lambda, and H lambda, H is complete symmetric polynomial. A complete symmetric polynomial is Sk. So this term becomes sigma special Schubert classes. Therefore, we obtain the following Jamberi formula. Theorem Jamberi formula. For any partition lambda contained in the rectangle, we have sigma lambda is a polynomial in the special Schubert classes. The polynomial is expressed explicitly given by the determinant sigma lambda I minus I plus J sigma diagonal entries sigma lambda 1, sigma lambda 1, sigma lambda 1, and this element 1, 1, 1. Sorry. Sigma, no, sigma lambda 2, sigma lambda r, and sigma lambda 1 plus 1, sigma lambda 2 minus 1. And we use a convention sigma k equals 0 if k is negative or k is greater than n. This is a Jambeli formula. So each Schubert class is expressed as a polynomial in the special Schubert classes. The expressed polynomial is given by this determinant. So example. When r equal to m equal to 4, so we consider Grassmann 2, 4. In this case, there are six Schubert classes. Sigma 0, sigma 1, sigma 2, sigma 1, 1, sigma 2, 1, sigma 2, 2. Sigma 1 and sigma 2 special Schubert class. One and sigma 2. For example, sigma 1, 1 is determinant diagonal entry sigma 1, sigma 1, sigma 2, and sigma 0, 1. Therefore, sigma 1 square of sigma 1 minus sigma 2. And also sigma 2, 1 is sigma 2, sigma 1. The sigma 3 is 0. Is 1. Therefore, sigma 1, sigma 2. And also sigma 2, 2 is determinant. Sigma 2, sigma 2, 0, sigma 1. So that's sigma 2, square of sigma 2. In this way, we can express each Schubert class as a polynomial in the special classes.
Excuse me, the lower left entry of the second matrix, shouldn't it be sigma 1?
Sigma. The sigma. It is sigma 0. Sigma. Not minus 1. Sorry. Sigma 0.
This is sigma lambda 2 minus 1.
2 minus 1.
Oh.
So sigma lambda 2 plus 1.
Yeah.
Yeah, so this is 1. Well, note that we can deduce this formula by the PL formula, also using PL formula. by the PL formula, sigma, the square of sigma 1 is 1 box. And by the PL formula, 2 plus 1, 2 sigma 2 plus sigma 1, 1. Therefore, sigma 2, sigma 1, 1. Sigma 1 square, sigma 2. And also, sigma 1 times sigma 2, 2 or 1, so sigma 2, 1. Sigma 1, sigma 2. In the same manner. Okay, so so in this way we can solve the structure constant problem and Jamberi problem in the case of the complex Grassmannian. And finally, I will mention the relation. I will mention summary.
Is that this ring homomorphism? The proof is easy. I mean, what sort of things do you need to prove this? The proof of this
Theta.
this data. This is a ring homomorphism.
Ring homomorphism, yes.
That's proof.
Proof is very easy. But for example, by the PL formula, so first we consider the case S lambda times S special, and then by the PL, yes, and additive theta is additive, theta S mu, by definition sigma mu. Then again PL, this is PL. PL for the Schubert polynomial, PL for the Grassmannian, sigma lambda. So the subring generated by special classes theta is ring hom, and since lambda r is generated by this special, yes, S1 S2 is complete symmetric. So as a whole, theta becomes ring hom. Yes. So summary, see also Manibel's book, Nolan Manibel's introduction. Okay, we can summarize these phenomena in the following table. There is a close relationship between the geometry of Grassmannian and symmetric polynomials. Grassmannian. Grassmannian and symmetric polynomials. And Schubert varieties Schubert varieties are indexed by partition. So Schubert variety correspond to partition. Wow, young guy. And the Schubert classes correspond to Schubert polynomials. Schubert polynomial is a good polynomial representative of Schubert classes. And the PAD formula is also PAD form. And Jamberi formula corresponds to Jacobi-Trudi formula. And intersections correspond to Littlewood-Richardson rule. So in this way, there is a beautiful correspondence between the geometry and algebra. So we would like to generalize these phenomena to other homogeneous spaces, such as Lagrangian Grassmannian or orthogonal Grassmannian, or more generally, we want to generalize this phenomenon to general G over P. Here G is complex, semi-simple, complex Lie group. For example, semi-simple Lie group, and P general parabolic subgroup. In the case of Grassmannian, G is GLNC or SLNC. Parabolic is block diagonal, block matrices. Okay.